Hello, it's Doodle here. In the world of programming languages, generally speaking, we can group them into two different categories. The first category are languages that are dynamically typed and typically interpreted. Sometimes these languages are referred to as scripting languages. The other category are the statically typed languages, and typically these will be compiled into real machine code or virtual machine code that then runs inside a virtual machine. One of the more prominent trends that we've seen with programming languages is one of convergence between dynamic and statically typed languages. We've seen, for example, that many dynamic languages have started to adopt some form of types, and this has been in a number of ways. For example, optional types, type annotations, and type hinting, to name a few. Meanwhile, in the statically typed world, we've started to see features such as type inference, in addition to other features, pop up that help the statically typed language feel closer to dynamically typed language. While there really wasn't any specific date when the dynamic languages started to become hugely popular, however, it was around the 90s and early 2000s that dynamically typed languages started to garner a lot of attention. It could be argued that timeline somewhat coincides with the rise of the internet. Developing for the web, dynamically typed languages offered a huge amount of flexibility as well as much faster development velocity. This speed allowed huge amounts of innovation as well as market disruption because the speed to market was dramatically revved up when compared to traditional development. The web was also the perfect delivery platform as web applications were always up to date and newer updates could easily be pushed out. Web applications are also device agnostic as they only need a compatible browser to use. However, this quote, move fast and break things approach, while great for the short term, came with a lot of costs for the longer term. In prioritizing short-term gain, one dramatically harmed long-term success. It is therefore not surprising that companies that started off with dynamically typed languages to build their platforms, when they've grown to become a larger company, have hit many obstacles in terms of managing their ever-growing complexity and productivity. What was once their key to accelerated development has now become their productivity imprisonment. Companies have resorted to many different approaches in order to face these challenges. Some companies, for example, have taken the bold step with great difficulty in rewriting their platforms from a dynamic language over to a statically typed one. While this has been the nuclear option, it is very expensive not only in terms of manpower but also a huge time sink, and not to mention the complexities involved in running two platforms in parallel while trying to reach feature parity. For some companies, the eventual rewrite was always on the roadmap as it was part of their original plan. So it was always understood that the first platform was always really a prototype, just enough to demonstrate the concept was viable. For those companies, while expensive, it was at least understood by all what the long-term picture looked like, and the pain was thus manageable. However, not all companies have such roadmaps, or more accurately, not even aware of the future technical debt they're getting themselves into, and are only faced with the growing pains as soon as the platform is no longer a one-man show. Exceptional companies such as Facebook that have grown far too rapidly could not practically do a rewrite because the codebase was essentially too large and the platform was too big to fail. These tech giant companies have resorted to either creating entirely new languages or to throw money at the problem by trying to alter the language or stack itself by adding types to nudge the dynamic language to behave more like a static language. When the discussion of types are brought up, the dynamic language community will often respond either by denying that types are needed, or they'll present testing as the solution to the problem of lack of static types and a compiler. It is not a big surprise that testing and TDD zealotry is most acutely found among the dynamic language communities. These communities will often say that testing is independent of the language, and there is some truth to this. However, it doesn't fully capture what is going on. Testing itself is of course a very broad topic in itself, perhaps one for another session. However, there are a few things to note here. There is a big difference between good useful tests and bad pointless tests. The kinds of testing that need to be done between dynamic and static languages are not entirely the same, even though there are some overlaps. Because dynamic languages are not compiled, this means that many things only happen during runtime. As a consequence, one could have completely invalid code happily sitting in production simply because that particular code path has not been executed yet. Of course, when it does get executed at runtime, it blows up and often in production at 3 a.m. Statically compiled languages simply never allow this to even compile, let alone get into production. The dynamic crowd will say they can solve this using linters, code analyzers, and a smothering amount of automated tests. However, this doesn't really solve the problem if we think about it. In order to get the equivalent guarantees, every single code path would need to be tested. In other words, 100% code coverage all the time, every time. Realistically, that simply isn't possible. The other thing to think about is that if we're adding linters, static analyzers, and creating 100% code coverage, then at that point, why would you not just use a compiler that would do all of that for you automatically? Granted, in a statically typed language, one does need tests. However, they are dramatically fewer, and the ones that you do have are related to intent and behavior of the program, and not things that the compiler can already guarantee for you. As the type system becomes more advanced, a lot of the problem domain can be directly modeled and encoded into the type system. This means tracking the mental model and hence state is offloaded to the compiler, and that complexity doesn't need to be manually tracked by the developer. In a dynamic language, we have to manually track that model through the codebase, and oftentimes this is why we see a lot of what is called defensive programming. That is because in a dynamic codebase, the types are not always known, and so a lot of checks have to be added in the code itself. This muddies the actual intent of a block of code and thus adds unnecessary code complexity. The types are not only enforced and guaranteed by the compiler, but they act as a form of single source of truth documentation. This helps hugely when using unfamiliar libraries, as one can be guided by the compiler in discovering the library surface. Finally, refactoring when you have a compiler that enforces the types is dramatically easier as compared to dynamic language, where you can never be confident your changes haven't inadvertently broken something somewhere you're not even sure of. Okay, so what's the conclusion? Should we all ditch dynamic languages and use static ones? No, of course not. Dynamic languages will always be faster and more productive in the short term. However, it's knowing that upfront and understanding the trade-off for your project scope. If you know your project will be something that can be grokked by a single developer and it will never grow larger, then using a dynamic language is absolutely fine. However, if you know that the code base is going to grow beyond a single person, be kind to yourself. Don't build your house's foundation on quicksand. Pick concrete instead. Anyway, that's all for now. See you on the next one.